So today we will discuss about design of shafts. Right. So as you know, most of the times this shaft is used for transmitting motion. Right. So what we are going to discuss is this transmitting shaft or transmission shaft. So as you can see in the figure, this shaft is generally stepped shaft. Right. These are the step shafts. As you can see here, steps are provided because most of the times gears or pulley are mounted in this middle region, right? So that is why this middle region is having that higher diameter than those region which is going to go inside bearings. Like these ends will most of the times go inside bearings. So at those places that higher diameter is not that required. Right. So you can see this way you are having your shaft constructed. So in this stepped shaft, you can also see wherever these steps are provided, at those places these fillets are used. So these fillets are used to reduce the stress concentration, right? To reduce stress concentration, right? So these are some of the basic things, right, related to this shaft. And generally whenever this circular cross section machine element is there, we are calling it a shaft. But in shaft also there are some different terminology is used, right? Some of those circular elements are called axle, some of them are called spindle, right? Let me write this spindle again. So this axle, spindle, right? Then you may have that counter shaft. So these are different terminologies according to the application of that circular rotating element, right? So axle is generally used when it is simply used to give support to some rotating element, right? So in that case it is not transmitting any torque, right? So only bending will take place in case of this axle, right? In our vehicle we are having sometimes this kind of axle where it is only supporting the rotating wheels, and even axle may be steady and not rotating. Sometimes axle may rotate, but sometimes you may find that axle is a non-rotating element, right? Like the next is the spindle. So spindle is generally used in those machine tools, right, to provide motion to your workpiece, right? So in machine tools, that short rotating circular element is known as spindle, right? And then counter shaft. Counter shaft is whenever you are using any main shaft on which your gears are mounted and you are providing motion from that shaft to other shaft. Here the word counter means it is rotating opposite to that main shaft direction. That is why it is known as counter shaft. And generally through gear this kind of motions are getting transmitted, right? So this is how you are having that various types of shafts, right? So these shafts, when you are designing, you are using certain criteria. So let us see, generally uh, it is used so most of the times you may use this strength based application only. Sometimes you need to go for based on rigidity, right? So we will see both what is design of shafts based on strength and what is design of shaft based on rigidity. So here as you can see, in case of this design of shaft based on strength, you are going to consider that normal and shear stress is acting on shaft while you are designing that shaft. You are designing that shaft means what you are going to design is you are going to define the diameter of that particular shaft in order to bear the stresses acting on it. So it may happen that your shaft may be under different stress conditions. Different stress conditions means there are different types of stress. There may be axial stress, bending stress, shear stress, right? So suppose if we are considering that uh, axial stress is let us say tensile, so it is that load upon area, and as shaft is a circular element, that area will be pi by 4 d square, right? So this axial stress may be represent with this particular simple equation, right? So after that we have seen that it may also be affected by, or it may be under the action of bending stress. So bending stress, you know from the theory of pure bending stress is given by mby upon I, right? So mb is that bending moment, y is the distance that is generally considered as d by 2, and this mass moment of inertia is this pi by 64 d raised to 4. Sorry, it may be area moment of inertia, right? So pi by 4 d square, and then again d square, that is this pi by 64 d raised to 4, right? So and this is bending stress, right? And there may be shear stress also. So shear stress also, you know from that theory of pure shear, your shear stress may be given by this
TR by J.
tr by j mtr by j, where t or mt is the torque, r is again the t by 2, and j is polar moment of inertia, right? So that is pi by 32 d raised to 4. So this way you are having this various stresses acting on your shaft. So it may happen that your shaft may be under the action of any particular stress, or it may happen that your stress is under the action of combined stresses, right? So suppose if you consider that case 1, right, where your that normal stress sigma x is that sigma t plus sigma b, means both axial and bending stress are acting, right? So in that case your this normal stress, you know, right? Normal stress are given by this sigma x plus sigma y by 2, where sigma y we are considering as 0, right? Plus or minus is under root of sigma x minus sigma y by 2 square plus tau square, correct? So this sigma
Yes,
y
sir.
we are considering 0, so it will become simple that sigma x by 2 plus or minus sigma x by 2 square plus tau square, right? So this is your principal stresses sigma 1 and sigma 2. Similarly, your maximum shear stress is also given by this relation, right? Because you from mover circle also, it is the radius of your mover circle, right? So sigma x by 2 square plus tau square will give you the maximum shear stress. So in case 1, this sigma x is the combination of both axial stress plus bending stress, right? In case 2, you can also consider that sigma x is only sigma b, means axial stress is absent, right? So in that case also you can have this maximum principal stress as well as this maximum shear stress. So here, as you can see, we are considering this normal stress and shear stress, right? So you know, I guess by now, how to draw this Mohr circle. So what you are going to do is you are going to first plot this particular point, right? This sigma x, actually this full is sigma x, right? Because here it is sigma x by 2, sigma x by 2, so this sigma x, right? So first you are going to mark this point, and from that point you are going to mark your that this particular tau, right? So after marking this, then you are going to join this both the point, right? Here this point B and point D you are going to join, and then you are going to take that EB as radius, and you are going to plot the circle, and when you are going to do this you will get your Mohr circle. So in that, this may be your sigma 1 and then this may be your sigma 2, right? And this is your maximum tau as it is mentioned here, which is equal to the radius of the Mohr circle. So this is already clear to all of you, right? Because this is sigma x by 2 plus square plus tau square, that is nothing but this tau max, that is this radius. So this is already clear to you, right? Hello.
Yes sir, it's clear sir.
Okay. Then once you have this normal stress and shear stress acting on it, then you can apply this different theories of failure, right? Theories of failure we are going to apply. So in that, first you consider that MPST, maximum principal stress theory. So according to maximum principal stress theory, first you have to have idea what are the stresses acting. So let us say if sigma b is equal to this 32 mb upon pi d cube, right? If you give simplification to whatever I have written above, it will be coming to this simplification only. So 32 mb upon pi d cube, and here it is 16 mt upon pi d cube. So once you have this sigma b and tau means bending stress and shear stress, then based on that you can calculate your that sigma 1 means maximum we are interested, right? So we are neglecting for now that sigma 2, right? So we are considering, because shaft is designed for the maximum stress it has to bear, so we are considering this maximum principal stress sigma 1, right? So this is sigma x by 2. Sigma x is equal to sigma b, right? So sigma x by 2 means 16 mb upon pi d cube, right? As we have seen earlier, it is 16 mb upon pi d cube, and here also it will be 16 mb upon pi d cube plus 16 mt, here it is square, right? Plus 16 mt upon pi d cube, this whole square both, right? So once you are done with this, you can further simplify that 16 by pi d cube, then it is mb plus under root of mb square plus mt square, right? So this is how you are having this maximum this normal stress to maximum principal stress acting, right? So this is your this equivalent actually moment, right? Equivalent bending moment, you can say, right? So this sigma 1 is equal to 16 upon pi d cube in bracket this mb plus under root mb square plus mt square.
सर ये इक्विवेलेंट बेंडिंग मोमेंट नहीं, टॉर्शन मोमेंट होगा ना?
Torsional moment will be there when you consider that maximum shear stress theory. So in that
ओके सर,
case you
ओके
will
सर.
have that equivalent torsional moment. Okay.
मतलब यहाँ पे 32 आगे नहीं था ना, तो इसलिए पूछ रहा था मैं.
Yeah, but here it is actually some in some of the books you may find that this equivalent bending moment as 1 by 2 of this, right? Because if you multiply and divide it by 2, then you will get 32 upon pi d cube, and here it will be 1 by 2 mb plus mb square plus mt square. Are you
ओके
getting
सर.
what I am trying to say?
यस सर, यस सर.
Okay, so here it is equivalent bending moment because we are considering this maximum
सर,
principal stress theory.
सर,
Yes?
सर एक एक स्टूडेंट एंट्री मतलब मांग रहा है क्लास में.
Yeah, 1 second. Right, so uh, no one is there.
मतलब अभी मेरे को मैसेज किया था कि एंट्री नहीं मिल रही है. ओके.
Okay, it is not here yet, right? If it will come, I guess, some kind of notification will come, so I will make him enter. Okay.
Okay, sir.
Yeah. So yes, so let us continue. So here, once you get this sigma 1, then according to that maximum principal stress theory, you can have this sigma 1 is equal to your SYT upon vector of safety, right? So this is how you are going to calculate or equate your this particular stress acting on your shaft in order to calculate the diameter of the shaft, right? So if you go for other failure theory, that is MSST, right, maximum shear stress theory. So in maximum shear stress theory, you are having this maximum shear stress sigma x by 2 will be again 16 mb upon pi d cube square, right, plus here it will be 16 mt upon pi d cube square, right? So this is how you are having your maximum shear stress. So here again you can take out this 16 upon pi d cube and you will have this mb square plus mt square. One second, now I guess someone is there. Okay, yeah. So as you can see here, this tau max is equal to 16 upon pi d cube and under root of mb square plus mt square, where this under root mb square upon mt square is known as equivalent torsional moment, right? So this is equivalent torsional moment. So once you get this shear stress, then you know that allowable shear stress is related to your yield strength by this relation, right? So allowed or whatever allowable shear stress is the half of the allowable that yield stress, right? So once you have this particular relation, then you can find your this tau max as this 0.5 SYT upon this factor of safety. So this is how you are having this both theories of failure which can be used while you are designing shaft based on strength. Okay. So
Yes, sir. Yeah.
okay, okay. So once you have this idea, then you can move to the next one, that is this design of shaft based on rigidity, right? So design of shafts based on this torsional rigidity, it means see sometimes some applications are having uh, other requirements, right? Every time it is not only the strength based on which you are going to design your the shaft, right? Sometimes rigidity is also required, because if you observe in some of the application like in crankshaft and all, there is rigidity in twisting is required, right? So twisting should not be done when your shaft is under operation. So when twisting should be restricted, it is going to come under this torsional rigidity, right? Your shaft should be torsionally rigid, right, in order to avoid that twisting of your shaft while it is transmitting the what you can say power, right? So twisting is not allowed. Similarly, sometimes deflection is not allowed, right? So in case of that deflection is not allowed, that is considered as some lateral rigidity. So based on the application of shaft, you are going to decide based on which criteria you are going to design your shaft. So in case of this twist is not allowed, as we have considered that crankshaft. So the important thing is that the theta, right? So as you know that this T upon G is equal to tau upon R is equal to this G theta by L. So from this, if you consider that G theta by L g theta by L is equal to this torque upon J. So this will give you that theta is equal to this torque. We can also consider it as mt, right, or the torsional moment. So this mt or T into L upon G into J. So if you consider that J is equal to pi by 32 d raised to 4, right, and then your G will be as it is, L will be also as it is, right. So if you, and one more thing you need to do is you need to convert it into that radian. So if you convert it, then that 180 by pi will be there. Actually it is in radians. Whenever you are going to convert it into degree, then it will be this 180 upon pi, right. So 180 upon pi into this mtl upon gj, right. So mtl upon g, and j as we have just now written that pi by 32 d raised to 4, right. So if you further simplify it, then that pi is there, right. So if you put values of pi and all and then give simplification, then it will be 584 mtl upon gd raised to 4, right. So this is how you are having this design of shaft based on rigidity, and in that also we have considered this theta, right, angle of twist. So this is how you are having this particular criteria, right. Then some ASME code is there, right. So there are certain things based on the different types of load acting, or the nature of load acting on your shaft which you are designing. You can consider this KB and KT. This KB and KT will be multiplied to your that MB and MT accordingly, right, while calculating your equivalent that bending and torsional moment. You know what is that equivalent bending
ये
and torsional moment, right.
सर ये चीज गेट में यूज होगी क्या वैसे?
Yeah, it can be used,
ओके
right. It will be given if it is required to do so, right.
ओके सर.
Yeah, so this is how you are having some different requirement, right. Now as you can see, one second, I guess. Yeah, so now can you see this one numerical is there? Can you see it?
यस सर.
Yes. So here actually you are required to design a shaft, right, which is having this kind of stresses and this kind of machine element it is carrying, right. So if you look at the problem statement, the layout of a transmission shaft carrying two pulleys B and C and supported on bearings A and D is shown in figure, this given figure, right. Power is supplied to the shaft by means of a vertical belt on the pulley B, which is then transmitted to the pulley C carrying a horizontal belt. Okay, right. Then the maximum tension in the belt on the pulley B is 2.5 kilonewton, and the angle of wrap for both the pulleys is 180 degree, and the coefficient of friction is 0.24. Now the shaft is made of plain carbon steel 30C8 and the factor of safety is 3. Determine the shaft diameter on strength basis, right. So now here what you are going to do at first place,
T1 by T2 equal to e की पावर म्यू थीटा.
okay. So you can start attempting this, right. Let us see what you are going to get. What I'm giving you hint is you have to first see what are the vertical forces acting on it and what are the horizontal forces acting on it, and then you have to calculate those vertical reactions and horizontal reactions, and then based on that you need to come up with your bending moment and torsional moment and all, right? So can you give it a try?
Yes, sir.
Yeah, so please go ahead. So this p1 by p2 is equal to e raised to mu theta, as you can see here. P1 by P2 is e raised to mu theta. Mu is given, right, as 0.24 and theta is given as 180. So here it will be e raised to 0.24 pi, right, and P1 by P2 is actually P1 is given as 2.5 kilonewton, right. Maximum tension is given as 2.5 kilonewton. So
Sir,
we can calculate
P2 आ रहा
P2. P2
है।
is,
Yes, sir. P2 1.176.
yeah, 1.176, right, or if you write it in terms of Newton, then 1176.47 Newton you can write.
ऐसे टॉर्शन मोमेंट आ रहा है 330.9
3
किलो न्यूटन मीटर।
30.9. If you give some little bit more decimal places, then I guess it will be better, because here this torque is P1 minus P2 into R, right. R is given as 250, right, diameter is given 250, right. So if you
यस
keep
सर।
it in terms of that Newton mm, then I guess it is coming this 330. It is
0.94।
2.5 Newton mm.
ओके।
So any other answer than this?
नो सर, यही आ रहा है।
Okay. All of you are getting the same?
Yes, sir.
Okay. Now the same torque is transmitted, right? So in case of that pulley C, P3 and P4 are there, right? So that P3 minus P4 into that radius of pulley C, here it is radius of pulley B, right. It will be equal to mt, which you have calculated, correct.
यस सर।
So here that RC is given, right, 125. RC is given as 125. So you can have this value of P3 minus P4 with you. So what is
2.47 किलो न्यूटन।
actually
47।
2647.06 Newton it is coming. Is it coming
हाँ।
like this?
ये यस सर, यस।
So once you have this, then you can again use that P3 by P4 is equal to e raised to mu theta for this also. So once you solve these two equations, right, A and B, you will get P3 and P4, right.
यस सर, यस।
So what is P3 and what is P4? P3 is 5000.
P4 had 2352।
2352, yes, it is almost
पॉइंट
this 2352.94 Newton. So
यस सर।
P3 will be 5000 then, yes or no?
यस सर, यस सर।
So once you have this calculation with you,
Yes, sir. Yes.
right, now you can neglect the weight of pulley, right. So the downward force acting at pulley B is P1 plus P2, right. Here this at pulley P, P1 and P2 are acting downwards, right. So this is P1 plus P2 at pulley B, yes or no,
यस सर, यस
right.
सर, यस सर।
So that will be, now what is P1 plus P2? What is P1 plus P2? Anyone? Hello.
Sir, 3.6762
Yeah, so it is
kilo.
3676.47 Newton, I guess.
Yes.
Okay. Then similarly, horizontal force acting at point C or at pulley C is P3 plus P4. This is P3 plus P4, right, which is going to act in the horizontal direction, right? P3 plus P4. So what is this P3 plus P4?
352.94.
It is 7352.94, yeah. 7352.94 Newton. Okay. Now the forces and this bending moment you need to calculate in vertical and horizontal planes, right? So you need to first make that diagram, right, like this for vertical. Sorry, this is for, yeah, vertical only, right? For vertical, this is the force, right, acting at B, that 200 from A and 800 from D, and it is 3676.47. This is 3676.47. So here you will have that reaction at A, vertical reaction at, what is that point, D or what?
A.
D, yeah, this point is
Sir,
D, right? Reaction at D, vertical. This is your point B, right, at which vertical force is there. So this is your vertical force diagram, right? Vertical force diagram. So from this, first you need to calculate this RAV and RDV, because this distance is provided, right? This is 200 and this is 800. Similarly, you have horizontal force diagram, right, in which it is acting at point C. So you need to calculate that reaction horizontal RA and reaction horizontal at RD. So this is horizontal force diagram, this is vertical force diagram. Horizontal force diagram, for that horizontal force diagram, the force acting at C is 7352.94. So now you can calculate, I guess, all these reactions, because here in case of horizontal you are having again 800 and 200, right, this distance, and this is 200. So you can calculate this now.
RAC आ रहा है 2941.18.
One second, one second, one second, RAV
Yes.
बताइए, हाँ,
2941.18.
2941.18.
D RDV आ रहा है 735.29.
ओके, 735.29.
बाकी कैलकुलेट कर.
ओके, करिए हॉरिजॉन्टल के लिए आप check it for horizontal. So done.
सर RDH आ रहा है 5882.35.
Okay, 5882.35. And RAH
1470.588.
1470.588. So from this, now once you have this what you can say forces with you, you can calculate the moment, right? So you need to calculate now moment at B, right, due to horizontal and vertical reactions, right? So moment at B due to this vertical will be what?
So could you repeat it
This
again?
this RAV into this distance will be moment at B, right? Vertical. Moment at B vertical will be this RAV into this 200,
Uh,
right? So what?
yes.
So what is
मेरा तो
this?
जीरो आ
Sorry.
सर आर डी वाई भी तो मोमेंट कॉज करेगा नहीं
No, no.
सर
When you
ओके
are
सर
drawing your that bending moment diagram, you are only considering up to this portion of the beam, right? So if you are at B, then moment at B will be this RAV into this 200,
ओके सर
right? Are you getting?
यस सर
So what is that
Answer.
value? Yes,
588236
588236 or 332 whatever. Similarly, you can calculate that MCV, because here also point C is there, right, at 200 from this. So and here also there is point B, right, which is at 200 from this point. So once you have calculated this MBV, you can calculate that MCV is equal to this RDV into 200. So what is this?
058
Sorry,
147058
147058.
यस
Similarly, you can calculate this MBH, that is RAH into 200, and MCH, that is RDH into 200. Yes,
पहला वाला है 2941117.6
7 point.
6
Okay, then here MCH
1176470
11,
76470
right? So once you are done with all this, then you have to calculate that moment at B and moment at C, right? Because it will be that under root of MBV square plus MBH square. Similarly, moment at C will be MCV square MCH square. So you can calculate this. Can you calculate and let me know what you are getting?
तो पहले वाले का आ रहा है 657 667.66
657.
667.66
These are all in Newton mm, right? So now MC.
वन वन एट फाइव
1185.
625.45
Okay, now see, we have calculated this both moment at B and C, right? And now you can see at B it is at C it is greater than B, right? Here MC is greater than MB, so we are going to consider that higher bending moment, because for designing any machine element you need to consider the maximum stress acting on that element. So here, as it is greater than MB, we are going to consider this moment at C, right, or bending moment at C for further calculation. Okay, so you have already calculated that torsional moment, right, MT, or no? MT you have calculated, right? This is your MT. You can see. Okay.
Yes, sir.
So MT is already with you. MC you have calculated, or that bending moment you have calculated. So now what you can do is you can apply that simple relation, right, for your the tau max is equal to the 16 upon pi d cube under root mb. Don't confuse with this mb, huh? This mb means not that moment at b, it is bending moment. Okay,
Yes, sir. Yes, sir.
anyway here it is capital B. Okay, is it okay?
Yes, sir.
Now what tau max we
Yes,
are
sir.
going to consider? What value of the tau max you are going to consider? So here based on maximum shear stress theory you are designing, right? Plain carbon steel is a little bit ductile material, so you are designing based on that MSST because shear stress you are using. So the tau max, if you remember, it is that 0.5 SYT upon factor of safety. Is it okay?
Yes, sir.
Hello.
Yes,
Yes,
sir.
sir. Yes.
So you are provided with SYT as 400 and factor of safety as 3. So your tau max will be this 0.5 into 400 by 3. Correct?
Yes, sir. 66.67.
Yeah. So now you can give simplification and please let me know what diameter you are getting. You are having all the values with you. You are going to use this value, right? Moment at C. So what are you getting as diameter?
Sir, 45.47 mm.
Okay, anyone else?
Sir, almost same, sir.
Okay, so this is how you can calculate your shaft diameter, right, when you are considering that design of that solid shaft based on strength. Now let us go for the next thing, that is design of hollow shaft, right, based on that strength basis. Now why hollow shafts are preferred over your solid shafts for certain applications is, as you can see, for that bending stress are distributed like this, right, as shown in the figure, right, and this torsional stress are distributed like this as shown in this particular figure B, right. So if you observe, the stresses are maximum in this region here, and here you can see similarly here and here you can see. So as stresses are distributed in that region, so instead of going for that full shaft, we can also go for this kind of hollow shafts, right? Because stresses are maximum in this region, right? Are you getting? Right? Hello?
Yes, sir. Yes, sir.
Right, so that is why we are going for this hollow shaft. And hollow shafts are also having certain advantages, right? Like for same weight, weight, yes.
Strength to weight ratio is high.
Sorry, strength to weight ratio is high. Yeah, that is also correct. So some of the other advantages are, for the same weight, actually hollow shafts are having that higher strength, right? Higher strength, right? Hollow shaft, hollow shafts are having higher strength for same weight, right? And higher that stiffness also, right? And natural frequency. So these are some of the advantages of hollow shafts over solid shafts, right? But we need to
Sir,
consider that for same weight we are discussing, right? So
सर इसका फ्रीक्वेंसी का फॉर्मूला क्या होगा?
sorry,
शाफ्ट से रिलेटेड नेचुरल फ्रीक्वेंसी का फॉर्मूला क्या होगा सर?
I guess it is in terms of that what we can say, the
मतलब
torsional rigidity. If we discuss, then in that case it is something, torsional stiffness is T upon theta, right? Like that, in that torsional vibration it is there. Otherwise, for this natural frequency, I guess this is only used. I am not that sure, but in case of the torsional vibration, you are having this T upon theta as that stiffness, and then that is used as under root that K by M or something like that, your equation of natural frequency, if I am not wrong. But still you need to check that, right? Are you getting what I am trying to say?
यस सर, यस सर.
Yes,
तो
sir.
ऊपर हो
Sorry,
जाएगा
sorry.
सर. मतलब अंडर रूट नेचुरल फ्रीक्वेंसी क्या होगा? अंडर रूट
KT by M, right? The torsional stiffness KT is generally calculated from this T upon theta.
यस सर, टी बाई
But still you need to verify, right? I little bit of that I remember that I'm sharing, but still verify that, okay?
ओके सर.
Right. So then some of the disadvantages are also there for hollow shaft, like it is costlier and it is going to occupy more space, right? So that are some of the disadvantages of this hollow shaft, right? So now if you go for that design of hollow shaft, right, based on that torsional rigidity, right, but actually before going to the torsional rigidity, we will first check with that our design of strength only. So in case of that hollow shaft design based on that strength criteria, if we consider that inner diameter to outer diameter ratio as C, then that normal stress or axial stress, right, axial stress you can consider as sigma T is equal to P by A, right, where this pi by 4 dO square minus Ti square, outer minus inner diameter square. And if you simplify this by considering this di by dO as C, what you are going to get is this pi by 4 dO square. If you are taking it out, then this 1 minus C square will be there. Di by dO is C. So like that you can get your axial stress. Similarly, you can also calculate your bending stress at this sigma b, which will be coming out this 32 MB upon this pi dO cube 1 minus C raised to 4. Similarly, shear stress also you can calculate the tau 16 MT upon is pi do cube 1 minus c raised to 4. Right, so like this you can write for hollow shaft, right? And once you have all this, then what you can do is you can again consider those case 1 and case 2, right? That case 1 where sigma x is equal to sigma t plus sigma b, and case 2, right, when you are considering sigma x as sigma b only. Right, now again you can apply those MPST and MSST. Right, in case of MPST, your sigma 1 is equal to this 16 MB upon pi du cube 1 minus c raised to 4, that MB square plus MB square plus MT square. Right, and again that sigma 1 is equal to that SYT upon Fs, and you can go for that MSST also, right? In that this tau max you are going to calculate, that is this 16 mt upon this pi do cube 1 minus c raised to 4 under root of mb square plus mt square, right? And then the sigma 1 is that the tau will be 0.5 SYT upon that factor of safety, 0.5 SYT upon factor of safety, right? So this is how you are having this design of this hollow shaft based on rigidity, based on strength. Now we will see that design based on rigidity. So in that also, that you can apply this T upon J is equal to this G theta by L, right? So if you put all the values in it, right, then you can simplify that this theta is coming as this 584 MTL upon G T O raised to 4, that 1 minus C raised to 4. So this is how you are having your this different relation, right, or different design equations, right? So once you are done with this, then you can solve this numerical, I guess. Yeah. So can you see this numerical? Hello.
Yes. Yes, sir.
Yeah, so here the numerical, what they have asked is a propeller shaft is required to transmit 45 kilowatt power at 500 rpm. It is a hollow shaft having an inside diameter 0.6 times of outside diameter. It is made of plain carbon steel and the permissible shear stress is 84 Newton per mm square. Calculate the inside and outside diameters of the shaft. So can you try and calculate this? Hello.
Solving.
Yes, sir. Yes, sir. Yes, sir.
Okay. So first you need to calculate the torque, right?
T omega.
Yes. So because power is given, right? So power is equal to T omega. So from that T is torque, right? We are considering it as mt also, right? So this mt
एट 859.44 TR है.
okay, power is given as 45 kilowatt, right? And then 2 pi n by 60, rpm is given as 500 rpm. So it will be coming 859
Point 0.44.
436.69, something like that, Newton mm. Okay, is it near to this?
Yes sir, यही है.
Okay. Then the C is given, right? Di by do, right? So di by do is what? 0.6, right? Because di is 0.6 times do. Okay. Hello.
Yeah. Yes, sir. 0.6, sir.
Okay. So now once you have this, then you can apply that direct equation, right, based on that torsional shear stress. You are having this equation, right? 16 mt from pi do cube 1 minus e raised to 4. Is it okay? Tau is
Yes, sir.
directly given as 84, right? 84, right? So here tau is given as 84. Mt you have calculated, C you are having, so you will find the TO from this. So what is this TO?
Sir, 39.12 mm.
39.12 mm. Now what is the DI? It is 0.6 times DU, right?
23.472.
Okay. Okay. So now this is how you can find this inner and outer diameter for hollow shaft. So is it clear?
Yes, sir.
Yes, sir.
Okay. Now let us go for some numerical or some previous year gate questions. So here the question is from gate 2003. Maximum shear stress developed on the surface of a solid circular shaft under pure torsion is 240 megapascal. If the shaft diameter is doubled, then the maximum shear stress developed corresponding to the same torque will be. So can you try this one?
सी होगा
Yes.
Sorry,
वाला होगा सर
क्या होगा?
30 MPa सी.
Okay, everyone is getting the
Sir,
same.
30 MPa.
Sorry,
Sir,
30.
30 MPa. 30 MPa, megapascal.
Right. Why? Because this it is getting doubled, right? And what is the
Double, sir.
relation? This T is equal to pi by 16 tau D cube, right? This is the relation.
Hmm.
Yes or no?
Yes, sir.
So
Yes, sir.
so from this, if T1 is equal to T2, then this pi by 16 tau 1 D1 cube is equal to pi by 16 tau 2 T2 cube. So from this, if tau 1 upon tau 2 is equal to d2 by d1 cube. Yes. So tau 1 is
Sir,
given
D2 by,
as 240.
pardon, sir.
Tau 2 you need to calculate. D2 is twice the diameter, right? So from this tau 2 will be 30. Is it okay?
Sir, D2 by D1 or D1 by D2? Oh, no, sir. D2 by D1.
It is correct only, right?
Uh-huh.
So 30 MPa will be your answer. Okay.
Sir.
Next is from 2004, a solid circular shaft of 60 mm diameter transmit a torque of 1600 Newton meter. The value of maximum shear stress developed. So how can you calculate this? Tau is equal to 16t upon pi d cube, right? Because t is equal to pi by 16 tau d cube. So tau is equal to 16t upon pi d cube. Yes or no?
सर ए 37.72.
So if you put this value, yeah, 16 into t, right, that is 1600 Newton meter. So this Newton mm, right? Then pi d is 60. So if you simplify it, you will get your answer around A. So all of you are getting it? Hello?
हाँ सर हाँ सर हाँ
Okay, okay. The next is a solid circular shaft of diameter 100 mm is subjected to an axial stress of 50 megapascal. It is further subjected to a torque of 10 kilonewton meter. Now the maximum principal stress experienced on the shaft is close to. So can you calculate this?
Yes.
Yeah. So first you need to calculate that shear stress, right? Because axial stress is provided as 50 megapascal, right? Axial stress is provided as 50 megapascal and torque is given, so that shear stress is also there, right? That 16T upon pi d cube. Bending stress is not there, but that 16T upon pi d cube, this 10 kilonewton meter, I guess then 10 into 10 raised to 6 if you convert it into mm, right? And then this pi d is
सर
what? 100 mm. So
tau would be 50.93 Newton mm square.
sorry, 50 point.
93 Newton millimeter square.
Okay, so this is 50.93 megapascal. So once you have
हाँ
the tau, then you can calculate this maximum principal stress from sigma x plus sigma y by 2, but here we are only having that sigma x. So sigma x by 2 plus sigma x by 2 square plus tau square. So you can plus yeah, from this
82 megapascal.
sorry,
With answer.
sorry, it is coming around
82 megapascal.
82 megapascal. Okay, all of you are getting the same?
ना सर मेरा ना आ रहा, मेरा तो रेडियस 14.76 आ रहा है सर.
Sorry,
Radius of the Mohor circle I am getting 14.
how
अरे
is it
नहीं.
possible? Because sigma x by 2 is 25,
Okay sir.
it is 50.
50 by 2. हाँ सर.
हाँ, okay.
हाँ सर अब सही आ रहा है.
Okay, so all of you are getting this as your answer, right?
आ रहा है, हाँ.
Okay, now next question is from the 2009. It is very straightforward question. A solid circular shaft of diameter d is subjected to a combined bending moment m and torque t. The material property to be used for designing the shaft using the relation this 16 upon pi d cube under root m square plus t square is. Tell me what will be your answer? Yes, anyone?
C sir. C.
Huh?
क्या सी?
C,
C.
right? C,
C, sir.
right? Torsional yield strength. Okay. The next is this match the following, right? According to that theory of failure. So you remember we have discussed this.
Yes sir. Yes sir.
Anyone can attempt this?
C sir.
Correct. Because P will be M, Q will be N, and R will be L. Correct. Okay. All of you got it? Hello.
हाँ सर. हाँ.
Okay, let us go to the next one. So it is from GATE 2012. A solid circular shaft needs to be designed and transmit a torque of 50 Newton meter if the allowable shear stress of the material is 140 megapascal. Assuming a factor of safety of 2, the minimum allowable design diameter in mm is. So can you try this one? Hello.
Yes sir. Yes sir. Doing sir.
First you need to calculate that tau, right?
हाँ सर. हाँ.
So tau is this whatever 140 given by this factor of safety 2. So 70 MPa will be your the
CR है sir.
stress. Sorry,
B.
Sorry sir, sorry sir.
B.
B, right?
B.
Yes, it will be B. Then it
15.37
ah
15.37 mmR.
yes, yes, yes. So it will be B only, because this once you have this tau, then tau is equal to this 16t upon pi d cube, right? So in that you will have this 70 is equal to 16 into your t is 50 Newton meter, so 15 to 10 raised to 3 Newton mm, and then this again pi d cube. So then d will be almost equal to 16 mm. Okay, okay. So now let us go to the next one, that is 2014 S3. It is also simple. Two solid circular shaft of radius r1 and r2 are subjected to same torque. The maximum shear stress developed in the two shafts are tau 1 and tau 2. If r1 by r2 is 2, then tau 2 by tau 1. Can you tell me?
0.5.
Sorry?
0.125.
You are getting the inverse.
8.
Yes, 8 is the correct answer, right? Because see, t is equal to pi by 16 tau d cube, right? So now as we have earlier seen, this tau 1 d1 cube is equal to tau 2 d2 cube, right? So from this your tau 1 r1 cube is also equal to tau 2 r2 cube, right? And from this your tau 2 by tau 1 is r1 by r2, that is 2 cube is equal to 8. Okay, okay. The next is 2016. So a shaft with a circular cross section is subjected to pure twisting moment. The ratio of the maximum shear stress to the largest
That
principal
would be 0.5. C.
no, no, no. Anyone else?
B आ रहा है.
Sorry?
B.
Yes, it will be B. Why? Because
Pure shear.
when you plot this pure twisting moment on your mover circle, it will be like this. Whatever plus normal stress is there will be same equal compressive stress will be there, right? So it is like this. So your maximum this tau max is this only, whatever this sigma. So it is same, right? This radius, this radius. So your this ratio of maximum shear stress to the largest principal stress is 1. Are you getting from this figure, Moore circle? Hello.
Yes, sir.
Okay.
Okay, okay.
Okay.
Yes, sir.
Okay. Okay. Now the next question is two circular shafts made of same material. One is solid and one is hollow. Right? Have the same length and polar moment of inertia. L1 is equal to L2 and J1 is equal to J2. Now both are
DR.
subjected to same torque.
D आ रहा है sir.
Okay. Yeah. Maybe tau s is less than, yes, correct. Right. So both are subjected to same torque, and theta s is the twist and tau s is the maximum shear stress. Right. So this question you will be able to solve from this T upon J is equal to G theta by L is equal to this tau upon R. Right. So if you consider the for theta, this T and J are same and L is also same. You can see this J, L, T all are same. So if you consider and focus on this T upon J is equal to this G theta by L, then you can say that this theta s is equal to theta h, right? So first part is clear, whether B or D may be the correct answer. Now the next is, if you consider the tau upon R is equal to G theta by L, right? So in this This L is same again, right, for both solid and hollow. So now this tau upon R for this hollow must be equal to this tau upon R for solid. Now this theta and L both are equal, right? So tau upon R for hollow and solid must be equal, right? Because this g theta by L is equal for hollow and solid. So here in case of this particular what you can say shaft, your radius of a solid shaft will be less than the radius of hollow shaft, right? Are you getting why? Because J is same for both. Js is equal to Jh. So pi by 32 d cube is equal to pi by 32 do cube minus di cube. Now if pi by 32 d cube is equal to pi by 32 do cube minus di cube, it means this diameter of solid shaft must be less than this outer diameter of hollow shaft. Is it or not? Correct? Hello?
Yes, sir.
Sir.
Yes,
Right.
sir.
So as radius of hollow shaft is higher, right, than radius of solid shaft, right, it will be lower than that hollow shaft. So in that case, this tau of H must be higher than the tau of S. So this tau S must be less than tau H. So this D is the correct answer. Are you getting it? Hello? Hello?
Yes, sir. Yes, sir. Getting that.
Okay, okay. Now next is this 2018 S2 hollow circular shaft of inner radius 10 mm, outer radius 20 mm, and a length of 1 meter is to be used as a torsional spring if the shear modulus of the material of the shaft is 150 GPa. The torsional stiffness of the shaft in kilonewton meter per radian is. So torsional stiffness, as I have just now told you, torsional stiffness is T by theta, that is Gj by L. Okay. So can you calculate this? Hello?
Yes, sir. Doing, sir.
Calculating.
Yeah, yeah.
So 35.34 into 10 to the power 3 Newton meter per radian.
35.34, yeah, is the answer actually. Right? So 35.34. All of you are getting the same or what? Hello?
सर नहीं मतलब आ रहा.
Check this once again.
मेरा तो कुछ पावर में आ रहा है. 35.34 into 10 to the power 9 आ रहा है.
So this kilonewton meter you must not have converted. You are getting it in Newton mm.
Okay sir, okay sir, okay.
Okay.
Sir, I also got into 10 to the 3. That's what.
So that you need to convert it into kilonewton meter. Okay. Okay.
Okay.
So let us go to the last one. Right. So here a shaft AC is rotating at a constant speed, carries a thin pulley of radius 0.4 meter at the end C, which drives a belt. A motor is coupled at the end A of the shaft such that it applies a torque mz about the shaft axis without causing any bending moment. The shaft is mounted on narrow frictionless bearings at A and B, where AB is equal to BC is equal to L is equal to 0.5 meter. The taut and slack side tensions of the belt are T1 is equal to 300 Newton and T2 is equal to 100 Newton respectively. Now the allowable shear stress for the shaft material is 80 megapascal. The self weights of the pulley and the shaft are negligible. Use the value of pi available in the on-screen virtual calculator, right? That is instruction anyway. Neglecting shock and fatigue loading and assuming this maximum shear stress theory, the minimum required shaft diameter is, right? So you need to assume the maximum shear stress theory, and you need to neglect that shock and fatigue shock and fatigue loading. So this shock and fatigue loading basically related to that kb and km, right, which we have seen on that table. So here you need to neglect it. It means you need to consider both kb and km as one, right, and you need to apply this msst, right. So you can first calculate the torque, right, based on this what we can say tension provided. So from that you can have this T1 minus T2 into R. So that is 80 Newton meter. Yes.
हाँ सर 80,000 न्यूटन mm.
Yeah. So 80 into 10 raised to 3 Newton mm, you can say. Now once you have this torque 80 Newton mm, it will also act at the other end also, right? So that is the same torque it will act. But in case of moment, if you consider that sigma of moment at A is equal to 0, then see because of that torque acting, you are having this reaction at both the end, right, as that 400, right, at both the end you are having this 400 Newton because of that torque acting, right, and I guess it will be in the opposite direction, right, so that it can create that couple, right. So once you have that torque acting, that reaction acting at both the end, and you will consider that what we can say this sigma of moment about A is equal to 0, then you can have that reaction at B, right, which you can calculate. So that RB into L is equal to this 400 into 2L, right. So from this RB can be calculated as 800 Newton, right. So and because of that you will get this particular RA also 400, right. So this is how you are having this particular what we can say different forces and what we can say moment acting on your this particular shaft. So
सर R upward होगा ना,
sorry,
upward की बजाय RA will be downward सर ना, 400 न्यूटन.
maybe, yeah, yes. In that case
R and RB both will be downward side.
actually RB may be downward, sorry, here in this
Upward.
case actually this RA and that RC may be both upward, this RB may be downward, right, like this. Okay, hello.
हाँ sir.
Yeah, so because of this RB it will be moment will be generated like this, and because of this it will be generated in counterclockwise. So here it is clockwise and here it is counterclockwise. So that we have made equilibrium, right? And then we have find that RB, right? So here
RB
once,
upward,
sorry,
RB will be upward sir, upward ही आ रहा है. RA downward आ रहा था sir.
but see this RA must be, then this vertical force must be equal to 0, right? All vertical forces acting must be
हाँ sir.
equal to
RB will be
0.
upward.
Sorry,
RB will be upward, RA will be downward sir.
okay. uh, yes, correct. Why? Because, yeah, why? Because here this at this point this T1 plus T2 is acting in the downward direction, right? So previously I have written this clearly, right? This is RC, right? Sorry. So this is downward. So this 400 into 2L, and here it is RB into L. So RB is acting upward. Yes, correct. And as this is upward, here it is downward. So here also it will be downward. Yeah. So this will be downward. Correct. Okay. So now it is clear, right? RA and RC both are downward. This RB will be upward. Okay.
Yes sir. Yes sir.
Okay. Correct. So now once you have all this data with you, then you can apply that MSST, right? Maximum shear stress theory. So what this theory says, that whatever your this equivalent torsional moment is there, right? KB and this QT into T torque square must be less than or equal to this pi by 16 tau dq, right? So you have all the data with you, right? KB and KT are 1. That bending moment and torsional moment you have calculated, right? Bending moment is 200 and torsional moment you have calculated as 80 Newton meter, right? Correct? Yes or no? See, this bending moment is 100 because this both the reaction RA and RC are what we can say 400, and this L is given as 0.5. L is given as 0.5. So 400 into 0.5 will be 200. Okay.
Sir, इसका answer 24 mm है क्या?
Sorry?
The answer to this question is 24 mm. Sir.
Almost, yeah, but we need to, I guess, give answer up to 2 decimal or something like that.
23.93.
23.93 or
हाँ
94.
23.93 आ रहा है.
Yeah. Correct. So this will be less than or equal to this pi by 16. This tau you have calculated, right? This 80 into 10 raised to 6 into d cube. So once you calculate this t, then it must be then greater than or equal to this 0.02393 meter. It means it should be greater than or equal to this 23.935 mm. Right, so your answer may be this 23.94 mm. 23.94 mm. Is it okay?
Yes sir.
Yes.